Thanks for the introduction. Sorry about the delay because the flash in the slides doesn't work on this computer here. So my talk today is mainly focusing on using a delayed frequency domain equalizer to try to compensate the crosstalk and coupling in a degenerated mode group division multiplexing system. As we all know that the differential group delay in the conventional multimode fiber is relatively large, which reduces the coupling actually in the fiber. So at the transceiver side, if we can selectively launch different channels into different mode groups, and also at the receiver side, we can selectively demux these the different mode groups into different channels, the transmission can be achieved without even using a MIMO DSP. However, due to the impairments in the mux and demux, the MIMO DSP is still required, and the complexity can be significantly increased when for longer transmission distance, which is again due to the large differential group delay. However, the crosstalk in the mode mux and demux only generate discrete impulses in the channel response, which will allow us to use a delayed equalizer that can reduce the complexity and also improve the system performance as all these inactive taps can be removed. Here in this diagram, I just try to briefly illustrate how the actual crosstalk and the coupling happens in the system and how this affects the actual channel impulse response, which is shown on the right-hand side. This is being estimated by using a least square algorithm. And on the left-hand side, in this Sankey diagram, the width of each tributary represents how much energy or power has been transferred between different mode groups. So when we launch two independent impulses at the two input of the system, we can see that there's a strong mixing between in the mode mux, which will distribute the power into different mode groups. And then the impulses have been propagating at different speed in the fiber. Again, at the receiver side, another strong mixing, and eventually all those impulses have been placed at different location in the channel impulse response with different amplitude. And the separation between different impulses is defined by the actual differential group delay in the fiber. And we can see that there's not strong, like the shoulder in between different impulses is relatively low, which means that the actual coupling in the fiber is not that strong. And all I want to say here is that with strong crosstalk in the mux and demux and the weak coupling in the fiber only generate discrete impulses in the channel response. So here's a more accurate estimation of the crosstalk or coupling in the mode mux, demux, and the fiber. The x-axis represents the Longchamp mode, and the y-axis is the actual received mode group. All the diagonal elements in the matrix are the power of the desired mode that we would like to receive, and all the other elements actually represent the crosstalk or the coupling. The darker the color, the stronger the coupling is. So we can see that actually most of the crosstalk happens in the demux and the mux between mode group 1 and 2, which is obvious because the mode profile between these two mode groups is overlapped quite a lot. And also the actual coupling in the fiber is approximately 10 dB lower than the crosstalk in the mux and demux. So in order to compensate all this crosstalk and coupling, we need an equalizer that has a sufficient number of taps to be able to cover the whole channel impulse response. However, due to the discrete nature of this kind of channel impulse response, some of the taps are actually inactive. And it only does is to include noise into the actual output. So in order to reduce this additive noise, we can actually remove all those inactive taps and replace it actually by using a delay which corresponding to the actual differential group delay of the fiber. So we can also view this type of equalizer, which we call it a delayed time domain equalizer, as three independent sub-equalizers. As those two types of equalizer operates in the same type of scenario, they both, the complexity of those equalizers both follows a linear relationship as the number of taps. And we need to point out that as the required number of taps for each sub-equalizer is still relatively large, which as people have shown that when the number of taps is large, it's better to implement it in the frequency domain, which can reduce the complexity. So here I just showed a conventional frequency domain equalizer with 50% overlap safe method. Instead of doing a convolution in the time domain between the tap coefficient and the input signal, the actual convolution has been done in the frequency domain by multiplication. After that, the signal has been transferred back into the time domain by using an IFFT, and then the errors can be calculated. And eventually, finally, the coefficients of the taps has been updated by using both the frequency and time domain data. As we all know that the complexity of a fast-forward transform follows a logarithmic relationship with the number of taps. So when the total number of taps is above 16, we found it's better to use a frequency domain equalizer that can further reduce the complexity. So now we have seen that the delayed time domain equalizer can improve the system performance by removing all those inactive taps. Meanwhile, the frequency domain equalizer offers a lower complexity with large number of taps. So the question is, when the required number of taps for each sub-equalizer is large enough, can we combine these two methods together? So here is our proposed delayed frequency domain equalizer. Similar to its two ancestors, at the beginning we divide this equalizer into 3 independent sub-equalizers. And again, the delay between them corresponds to the differential group delay of the fiber. Again, we use a 50% overlap safe method to transfer the data back into the frequency domain to do the convolution. And after that, the actual output is a combination of the output from different sub-equalizers. I need to point out here, because in order to do this summation in the frequency domain, the block size for each of the FFT blocks has to be the same. Again, they can share the same error correction blocks as well. And after that, the actual coefficient has been updated in the same scenario as in the conventional frequency domain equalizer. It's obvious that as we use the fast-forward transform, so our proposed method has also followed a logarithmic relationship between the total number of taps for the complexity. And we found that when the total number of taps is above 64, the delayed frequency domain equalizer offers a lower complexity. Even though the complexity is still slightly higher than the conventional frequency domain equalizer, we will show that in the following slides, this method offers a better system performance as it removes all the additive noise coming from the inactive taps. So in order to compare the system performance, we use a 2x2 multi-group division multiplex system. At the transmitter, we're using 28 gigabaud QPSK signal, and we're using a spatial-light modulator to multiplex these two signals into LPO1 and LPO2. Then it's been transmitted through 8 kilometers graded index multimode fiber. At the receiver side, another SLM demux has been used to demux the signal back into 2 independent coherent receivers. An 8-channel real-time scope has been used to capture the waveforms, which is sampling at 80 gig sample per second. And all the 3 different equalizers have been applied offline using MATLAB. So here on the right-hand side, I showed I plot 2 Q-factor curves as a function of the total number of taps using the conventional time domain equalizer for both model group 1 and model group 3. On the left-hand side, I just put the channel impulse response as a reference. So we can see that when we increase the number of taps, the system performance has been improved. And this is due to the fact all the central impulses have been covered by our equalizer. Further increase the number of taps, we see there's a slight jump in the Q-factor curve on model group 3. This is due to the fact that the first post-cursor impulses has now been covered by the equalizer, which improved the system performance. Keep increasing the number of taps, another jump has been observed in the Q-factor curve for model group 1, and this is due to the first precursor impulses being covered by the equalizer. Keep increasing the number of taps, actually we see a degradation of the system performance as we see these 2 negative slopes in the curve. And this is due to the noises in between the first and the second post or precursors has been included into the output. Finally, the best performance is being achieved when the equalizer covers all the channel impulses. And we found that the total number is about 563, which is way higher than 16, as I mentioned earlier. So it's better to implement a frequency domain equalizer that can reduce the complexity. This performance actually from the frequency domain equalizer follows exactly the same trend as the time domain equalizer. The reason that we only selected individual or discrete number of taps is because fast-forward transform operates more efficient when the size is a power of 2. So in order to get rid of this additive noise between the impulses, we can actually use a delayed time domain equalizer. Here we show the improvement of the system performance, and we can also see that at the very beginning, all the channel impulses has been covered, so all the jumps in the Q-factor curve has been removed. It still suffers the same issues when you keep increasing the number of taps. It will include the noise that are from the inactive taps. However, the best performance was achieved by a total number of 321 taps. Again, this is higher than 64 as I mentioned earlier, so it's better to actually using a delayed frequency domain equalizer. Here we see the performance follows the same as the delayed time domain equalizer, which is approximately 0.1 to 0.2 dB higher than the conventional frequency domain equalizer. Here we set two targets, Q factors that we want to see in order to achieve this target, what is complexity by using these three different type of methods. It's obviously that the conventional time domain equalizer requires the highest complexity. By reducing all those inactive taps, we can see that the delayed time domain equalizer offers a much lower complexity compared to the conventional time domain equalizer. This complexity can be further reduced if we can independently optimize the number of taps for each sub-equalizer. But however, the lowest complexity actually is offered by using the delayed frequency domain equalizer, which is approximately 2.8 times as the optimized delayed time domain equalizer. Even though the complexity is still slightly higher than the conventional frequency domain equalizer, and we can see on the left-hand side, by using the conventional frequency domain equalizer, this required Q factor can never be achieved. So in order to conclude, the crosstalk in the mode mux and demux only generates discrete impulses in the channel response, which will allow us to use a delayed equalizer that can improve the system performance as we can remove all this additive noise from the inactive taps. As we found that the required number of taps for each sub-equalizer is still relatively large, so by using a delayed frequency domain equalizer, the complexity can be further reduced. And also it maintains the same advantage as the delayed time domain equalizer, which has a better performance. There's an interesting talk on Monday afternoon which shows that the actual mismatching in the splicer also generates discrete impulses in the system, which means this method can also be implemented to tackle the issue of the mismatching in the splicer. Thank you.